In this video, we want to digest what exactly was happening as you were constantly adding thermal energy to an ice-water solution.
As you can see at the start of this experiment, I've got ice and water. Ice is at, when it's mixed with water, a starting temperature of 0 degrees Celsius. Notice the hot plate is not on because the drops aren't evaporating. Here's a little while later. Now the hot plate's been turned on, and you can see if I put some water onto the hot plate, it's going to start to fizzle away in steam. We are now adding thermal energy at a constant rate. Thermal energy has been added now for quite a while, but the temperature is just not going up. Why is that? Why is, if we add thermal energy at this constant rate, does the temperature not go up?
First, I want you all to think about the difference between thermal energy and temperature. Remember, thermal energy is the total amount of kinetic energy or vibration of all the molecules, while temperature is, on average, the kinetic energy of all the molecules. So they're not the same. They're similar, but they're not the same. So if you're adding thermal energy at a constant rate to a solution that has both solid and liquid, what's going to end up happening is the thermal energy isn't going to just disappear. It's going to be used for what's known as phase change. It's going to go into the solid, so the kinetic, or the solid is going to gain that kinetic energy, and it's going to be used to snap all of those bonds. And slowly, as those bonds are broken, then the thermal energy is going to be start to be used to increase the temperature.
Now you can see the ice is really starting to melt. And if you look at the temperature on the left side, you can see that it's increasing. And that's because almost all of the ice is melted. So some of that thermal energy is going to start to be converted into a temperature increase in this solution. Now we can see that all the ice has melted. We have one phase, liquid. When you have a single phase, thermal energy begins to be used as a way to increase the temperature. There are no bonds to be broken, so all of that energy is going into an extremely rapid temperature increase that just so happens to be a linear relationship, meaning a straight diagonal line. Do you remember what the boiling point of water is in degrees Celsius? To give you a hint, this is fresh water too. You said 100? You are correct. So, as you can see, this is almost reaching its boiling point. Notice that inside the beaker, bubbles are starting to form. That's because molecules are vibrating around so unbelievably violently that they're starting to crash into each other and shoot each other so far away apart from one another that they become a gas. A gas is molecules that are just going to be really moving fast and far away from each other. Notice that at the top of the beaker, you start to see steam forming. And we are about to hit the boiling point. There it is. We hit the boiling point. Look at what starts happening to the beaker now. Now there is a massive phase change going on. And it's going to, well, notice that it's peaking up over 100. And it's probably because this beaker wasn't 100% cleaned out properly. Make sure you guys clean out your beakers. But, whoa, look at that. Insanity. Phase change. But it's leveled out again. So when there's one phase, there's a temperature increase. Thermal energy goes to temp increase. When there's two phases, thermal energy goes to phase change. So what does this look like on a graph? Well, first let me start off by adding some numbers to my axes. You can see the y-axis is temperature in degrees Celsius and the x-axis in time in minutes. And our x-axis down here, it actually represents a constant addition of thermal energy. Constant therm energy. That's what's going on. So I'm going to add 0 degrees Celsius here and 100 right up there. So when you start, you have two phases. You have both inside of a beaker, you've got water and ice all on the inside. When you start adding thermal energy at a constant rate, all of that energy is going to phase change, and therefore it is not going into temperature increase. So you see a flat line that happens. That's what's going on the first, few minutes or so. Eventually, we get to a point where now all of that ice is melted and you're left with just liquid water. At that moment, because there is no more ice, it's only one phase, all thermal energy goes to temperature increase. So we see a line, a very rapid line shooting up, going up, until you reach the boiling point of that substance, which for fresh water is 100 degrees Celsius. Now, at that moment, we've got not only liquid water, but we have gas. Sure, all those dots represent gas leaving. Why not? That's steam. And because, again, you have two phases, you're going to undergo phase change, so it's going to level out at that temperature. This is what a phase change diagram looks like. A flat line to a straight diagonal line to another flat line. Now, I will say, in actuality, there is some curve that happens right down here and right up here. But it's okay to represent this as a very rigid line, line, line. Completely acceptable to do that. So here's our phase change diagram for fresh water, fresh H2O. And as we're going to learn, all different substances have their own phase change diagram, but believe it or not, they look the exact same. Slightly. There are some exceptions, but we can talk about that. So I'm going to expect you guys to be able to look at one of these and identify a bunch of different features on that. First off, the easiest thing to identify is when you've got a flat line, you know that you've got two phases, and you know that thermal energy is going to change of phase. When you have a diagonal line, you have one phase, and thermal energy is going into temperature increase. Okay, so let's wipe this clean. So, down here at this bottom line right there, which phases is water in? Well, if you look at the temperature, you can easily find out which one you're in. It's going to be at 0 degrees Celsius, which is known as the melting point or freezing point of water. All different substances have a bunch of different melting and freezing points. It all depends on their chemical structure, which you'll learn more about in chemistry. Up here is our boiling point. That's the first thing. You should also be able to say that, melting and freezing point, the two phases are solids turning into a liquid. And up here, your liquid is turning into a gas, where in the middle, all you have is just a liquid. Okay, now here's a challenge. What if I take all of this away? Gone, go away. More work than I anticipated. Gone. And now I'm going to set my 0 to be here and my 100 to be here. And I'm going to say I'm also going to constantly add thermal energy to water. But this time, I'm going to add a few more lines. First, I'm going to add a line that's here. Then I'm going to add a line that's here. And so on. Just like that. Well, what is that? Well, if you look very closely, it's the exact same graph. This little section that I just boxed in right here is the same graph that we just saw. I've now added this line and this line. What could those be? Well, think about it for a second. Here, solid was changing into a liquid. On this straight line, it was nothing but liquid. Here, liquid was changing into a gas. So what do you think is happening on this straight line? Did you guess that it was a gas and only a gas and temperature was increasing? You're right. What about down here? Take a minute. Solid. Only a solid. Rules don't change just because it's in a different part of the graph. It's going to be a diagonal straight line is one phase, a horizontal flat line, that's another. That's two phases, one going to another.
So I'm going to leave off right there for now. I'm going to make another video that's going to go a little bit more depth into this. But we're going to do some practice looking at other phase change diagrams because, like I said, it doesn't matter on the substance. We use water in class because water is just honestly the easiest and it has a really short window of melting to boiling points. So we're going to see that other substances do the same thing, they just have different melting and freezing points and boiling points. And that if you're taking energy out of the system, the rules still apply, it's just in reverse. When there's a flat line, you're going to have phase change, maybe this time from gas to a liquid if you're cooling it down, and vice versa in all those wonderful kind of ways. So, hope this was a little bit helpful. I'm going to do another video in a few days that'll add a little bit more to the story. See you guys all in class.